All of you came today thinking you're going to hear a particular announcement. Several years ago, we started this endeavor to create single-chip mobile application processors. And the reason why we did that was because we felt that the future of computing would come in all kinds of varieties. The PC will still be amazing computers. As we just mentioned, the cloud will become a very important computer. Your data center is going to play a greater and greater role in how you and I enjoy our daily computing experience. But we also felt that everything will very likely become a connected computer. Your cell phone, obvious. Tablet, it is obvious now. But your car will become a computer. As you see, the LG television is a computer. All of these devices needs to be powered by sophisticated, low-power mobile processors. And so we started the effort several years ago, and we introduced, and we thought that performance was really important, that these operating systems need performance, that resolution requires performance, and so we took the lead in building faster and faster mobile processors. We introduced Tegra 2 at the time. People thought we were kind of crazy. Why would you need a dual-core processor for a mobile processor? And if that wasn't crazy enough, well, we made Tegra 3, the world's first quad-core. And each generation, we took a performance leadership position. Well, ladies and gentlemen, today, to probably great surprise to all of you, I'd like to introduce the Tegra 4. Tegra 4 is nearly the worst kept secret, and the reason for that is because we had to start talking to our customers about it, and the enthusiasm became so great around its introduction that specs of Tegra 4 floated everywhere, and we immediately received quite a bit of questions. The first question is, how much performance does a cell phone need? I'm reading books fine, I'm listening to music fine, my UI is just fine, I'm reading magazines fine, everything works, movies work, everything seems to work. How much performance does anybody need in these mobile devices? Well, if you ask us, we need a lot more performance. We just need a lot more performance. And here today, I'm here to prove it to you. I'm here to prove to you that we need a lot more performance. Tegra 4 has 72 GPU cores. This thing is flooded with GPU cores. I just wish we could flood even more GPU cores in here. The second thing is, it is the world's first quad-core A15. Quad-core A15, which is ARM's new CPU architecture, and quite a bit faster than our last generation. We still have our power-saving core, this low-power core that hums along, sips little bits of power when you're mostly doing low computing requirement work while you're reading a book or just browsing a website or something like that. And then, of course, every mobile processor in the future will have to be connected. And 4G is obviously the next step. It includes a 4G, NVIDIA's first 4G LTE modem. Now, the first question I'd like to answer is, how fast does fast have to be? How fast does fast have to be? And why is it that we're not fast enough? And so, to show you, I would like to bring out the fastest tablet, Android tablet in the world today, let's put it into a foot race on doing something that is very everyday. So what I'm going to do is I'm going to show you two tablets, one Nexus 10, the Samsung Nexus 10, and the second one with Tegra 4, and they're going to go through and load 25 web pages. 25 web pages. And I don't know how many of you are out there that wish loading web pages were just snappier. But I just all day long wish I could load web pages snappier. And so let's put the two of them to a foot race and see how they do. Now both of these guys are so that we could eliminate any uncertainty that comes along with the internet. We have the web pages fully loaded, and both of them are pulling it off of a server across over a router. So it's effectively like a controlled internet experience. So can you show us now, please? And so this is on the left is the Nexus 10, and we're going through websites here, Amazon's website, CNN, New York Times, and on the right is Tegra 4. And we're cranking along. And these are web pages that you see that everybody uses on a daily basis. And if it's not clear already, the Tegra 4 is doing quite well. And so it took about 27 seconds to load 25 unique web pages. And the Nexus 10, let's give it a chance here. Okay, there you go. We're just delighted they finished. So that gives you an example, a real-world example of an application that we do all the time. Now, of course, all this basically means is this. If you're loading a website with Tegra 4, it comes up in a second, basically like that. If you're loading a web page with the fastest Android tablet in the world today, highest-end Android tablet, Nexus 10, it would take 2 seconds. Now, frankly, I think 1 second is well, it's twice as fast as 2 seconds. And if I'm going through web page after web page after web page, 2 seconds really is something that I would like to improve. There's so many other tablets we can compare to, and I won't torture us with all of those. But Tegra 4 is the fastest application processor, fastest mobile processor in the world today. And if you compare it to iPad 4, which is an incredibly fast CPU, it also has the benefit that every web page in the world is becoming optimized for the tablet. And even then, we're able to beat the iPad. Nexus 10 is the next fastest one, and then the Qualcomm 8064 Droid DNA behind that, and then Kindle behind that. And so relative to a high-end HD tablet today, Tegra 4 is somewhere between, an Android tablet about 2 times faster to about 3.5 times faster. Now the question is well, gosh, that's one application. It's a very large application, no doubt, but it's one application. One of the things that I've always loved, and I wish we would have created this technology for our summer vacation. Over the holidays, for our kids' graduation, we took Spencer and Madison to Europe, and my job was to take pictures of the kids and to document all of this. And when we come back, we're going to create a photo album, and that would be our graduation present for the two of them, and how they spent the last summer with their parents. And so everywhere I went, I was taking pictures. And of course, we're going through Europe, and we're visiting all these great places. But when we're visiting all these great places, it's during daylight. And when you're outside during daylight, the dynamic range of your phone, which has become my most important camera, simply isn't enough to be able to deal with it. And what was frustrating to me, and I kept sending emails back to the engineers, that gosh, we got to make HDR faster, we got to make HDR faster, we got to make HDR so fast that I can always use it as my camera. And the reason for that is because in life, you only get one shot. You only get one shot. There are so many experiences where we only get one shot. And because our camera is now our phone is now our most important camera, the ability to capture that magical moment comes and goes. HDR today our cameras today really needs to be improved. And let me illustrate that. So this is B. This is one of our employees, and she's standing in front of a tinted window, just to make it even possible to take a picture of her standing against bright sunlight. She's standing against a tinted window, and obviously you look. She's perfect. She looks beautiful, and she's well taken. It's a nice camera. This is the iPhone 5. However, you can't really tell what the outside is. It's completely washed out. It's washed out because the dynamic range of our camera, the iPhone 5, doesn't allow us to both capture her fidelity in the dark and the bloom outside, the extremely high, the bright sunlight outside. And so you could solve this problem by focusing on the outside. And this is what you get. Now you realize that you're in Las Vegas, but unfortunately, B has disappeared. And thankfully, there's a great new technology. This great new technology is called HDR. HDR works in most of the superphones today. They all have some kind of capabilities around HDR. And with an HDR shot, this is what you get. Quite frankly, it's a nice photograph. It's a nice photograph. She's very beautiful. She's standing in front of the palms, and everybody knows that she is enjoying a trip in Vegas. Now she goes outside, and she's standing out in the middle of the sun, and as you can see, all of a sudden, everybody behind her is washed out. Still a very nice picture. The sky's gone, the building's gone, and apparently some alien is walking just behind her. And so her boyfriend says, well, I have the technology for that. I have the technology for that. That technology, I'm a photo enthusiast. I know my stuff. I understand high dynamic range. I'm going to turn on HDR. Well, this is what you get on an iPhone 5. Well, the reason for that, now you see the background. But because the camera took 2 shots, and because there's movement in the back, it's very difficult for the camera, the image processing technology software, to now realign and figure out what's the best way to put the picture back together. Today's camera works like this. It's a sensor, goes into an image signal processor, which takes what is called the Bayer patterns and turns it into RGB. In the process, it enhances the image quality, extracts the lumens, extracts the chroma, and reconstructs what looks like to you a JPEG image. That JPEG image is stored into system memory, after which the CPU can come back and do some wonderful magic with it, such as HDR. What NVIDIA's Tegra 4 architecture does is something radically different. We introduced a brand new way of designing our chip so that we could put our processors closer to the imaging pipeline. The first thing that you see, and let me just go back, this is old, this is new. The first thing that you notice is that we take 2 shots at once. We take 2 shots at once. 1 shot with high exposure, 1 shot with light exposure. Then the first thing that we do is we dump it into this computational photography engine sitting in system memory. And once we do that, this engine could now take advantage of all of the processors on our chip. That's why we have 72 cores, that's why we have 4 A15s, that's why we have this powerful ISP. And with this computational photography engine, we could do the necessary mathematics so quickly that effectively at the end of the shot, you have HDR. Let me illustrate. If you look at it today, there's B standing in front of the palm, takes the first picture, goes through the sensor, goes through the ISP, goes into memory. Changes the exposure, that's what the HDR software does, changes the exposure, goes through the sensor, goes through the image ISP, goes into memory. Then the CPU fetches both of those images back out of system memory and does registration, does necessary warping, basically is taking 2 images, trying to align them pixel by pixel. Obviously very, very hard if your hand's shaking, if the subjects are moving. But nonetheless, it does its best possible job to register, to align, to warp everything so that it fits nicely together. And then it has to take this very, very large dynamic range effective photograph and retone map it down into something that can fit within one photograph's dynamic range. Okay? All of that mathematics takes time. In the case of the iPhone 5, it takes about 2 seconds. It takes about 2 seconds. And that's why if you're standing perfectly still, you take a great photo. If you're moving around, it's a problem. 2 seconds is a very long time. Well, the way that Tegra 4 does it is we go bam, bam. We take 2 shots. 2 simultaneous shots. And then all processors are deployed and running to do the alignment, the warping, the registration, the tone mapping, all of the necessary image processing, and boom, goes out one single photo. It basically is a one-shot HDR. As a result, whatever photograph you could take with a one-shot camera with one exposure, you could now take in HDR. Whatever you could take with one exposure, you can now take in HDR. And if you think about this architecture, imagine what else you could do with it. But before we do that, let's demonstrate. Let's demonstrate what Tegra 4's magic camera can do. Okay. Well, I understand that we're in Vegas, but we decided to go to Tahiti. And I'm taking a vacation in Tahiti, and I've invited a gamer. I met a gamer at Tahiti, and I noticed that we have a lot in common. And her name is Holly. And Holly, I understand that you like to play video games.
I do.
What are your favorite video games?
Skyrim. I like everything Star Wars. Red Dead Redemption. Anything RPG.
Like all the gamers out in the audience are going, wow, gamers ain't gonna look like that. Well, anyways, Holly and I turned out, we hit it off. We have a lot in common, and so why don't we invite someone to take some pictures of us? Okay. So Brian is the chief architect of our computational camera. Brian Cabral, sir.
How you doing, Jensen?
Great to see you. I understand that you have a camera you like to. This is a prototype camera. It's a prototype tablet. And you would like to take some pictures of us.
Yeah, yes, I sure will.
Hang on a second. I want this one to look good.
Take it off, Jensen. There you go.
Yeah. Make sure I'm standing there.
Yeah.
Right here.
Yeah. We can see it's all washed out. And let's just check out what we can do with some live HDR here. That's a lot of light being thrown out behind the...
Let me see if I understand what you're doing. I can barely see it through the reflection of that glass. But you're basically running HDR in live video right now.
All that computation that Jensen was talking about.
Wow, that's real amazing. So you're running in live video, and you're doing HDR on, let's see, on the right side of the
left side.
Your left side.
My left side.
Yeah. I'm talking their right side.
So let's take a picture.
Okay. So real. All right, I'm gonna try to look good. Come here, Holly. Hang on a second. Come here.
So let's get you all set up here. Are you good there?
All right, let's check it out. Thank you. Let's check that out.
Yeah,
Holly turned out good.
Let's check it out. Zoom in. Yeah, there you go. Could you focus it? Yeah, there you go.
Wow.
That's a keeper for your vacation.
Wow. Okay, so let's see what happened here. Basically, without HDR, the background is completely blown out. But with or we could focus in on us, or we could focus it on the background, but unless otherwise we would be underexposed. With this one-shot HDR, Brian was able to keep HDR running all the time, and he could do it while video's running, and he could take a single shot. And gosh, every shot from now on is going to be beautiful, and we can keep our memories forever.
Yeah, it's instant. It's always on. That far less than a second.
That's fantastic. Thank you.
Thank you.
Congratulations.
Thank you.
Okay, so Tegra 4, this new computational engine. There's so much you can do with this architecture. You saw the one-shot HDR today. You saw the HDR video. There's also HDR preview. It doesn't record it, munch on it for a while. It's recording, it's previewing all in HDR. But one of the things that is really fantastic, you probably didn't pick it up. Because we're doing everything at the software and hardware layer inside our chip, what comes out of the chip right off the bat is HDR. What that means is every software application today just works. No modification necessary. No porting necessary. You could either decide, I would like to have HDR on all the time, and then as a result, in that particular case, it was just a Google camera that came off of Android, pure Android, and it is fully HDR. The other thing that we didn't have to do just now, and I don't know if you did, was to turn on the flash. When you take two shots, how do you know when to flash? In the particular case that we have, we took one shot, then the flash works again. So you can use the flash in dark environments, turn on HDR all the time, works with every single application. The future of computational photography is quite exciting. This architecture is the first implementation for us, but you could just imagine Tegra N+1, Tegra N+2 will continue to innovate around this area. Some of the things that I'm excited about in the area of computational photography is really to turn your camera into a device that can take pictures far beyond what DSLRs could do. Just as digital music players made it possible for you to enjoy music, not just in a digital way, but in a way that you couldn't enjoy with CDs, cameras will do the same thing. These cameras, with these supercomputers, if you will, behind them, will do amazing things. HDR panorama would be possible. Wouldn't it be great when my kids were taking their karate black belt tests and they were doing their final performance? I would have loved to take a stroke motion of them. When they when they jumped up in the air and did a triple somersault, it would be fantastic to see their flipping kicks and capturing in a stroke motion example. The high dynamic range is a picture that Spencer took this summer, and of course we could also do 3D reconstructions. You take multiple shots of an environment, reconstructs the 3D space, and as a result you can look around. One of my favorites, the ability to continue tracking an object so that it stays in focus. Really, really hard to do that with a camera today. So if you're following your kids as they're playing soccer, the odds of being able to use a camera, a digital camera, to capture an action shot, impossible. But now, with computational photography, we could create technology that makes it possible for us to capture those magical moments. Computational photography, a brand new area that Tegra 4 is going to be able to take us into. I'm super excited about it. Video games. You know, you can't come to a NVIDIA event without talking about video games. Video games. Tegra really started this whole movement around really, really rich games, even for mobile devices. We created a store called Tegra Zone, which allows us to curate great games and make them available in an organized way and present it to gamers all over. Every single game has been optimized. Every single game has been tested rigorously so that when you download it, it just works. Whether it's Tegra 3 or Tegra 4 or Tegra 2, it just works. Our engineers have worked with the developers to take full advantage of the platform, and our engineers have worked with the developers to fully test it across all of the various devices that we're shipping. We go through great pains so that we could help gamers enjoy the games at its full capability, and also to help the game developers realize their imagination in the best possible way. Tegra Zone has been downloaded 6 million times. 6 million times. We're just so proud of it. And to Tegra Zone is to Tegra what GFE is to GeForce. That's one way to think about it. And so with that, let me introduce a new game that we've never seen before. And take it away, please. Dead Trigger 2. I guess that metal underwear didn't help. So Dead Trigger 2, thank you very much for that. We're going to save a few. Give me a moment, okay? Give me a moment. I'm going to save a few for you. But let me finish Tegra 4. There's something that happened about 18 months ago. We met a company that was working on this really, really cool technology. And it really connected with us because we were, you know that we've been in the computer graphics industry for 20 years, our company has, and many of us have worked on computer graphics much longer than that. And we came up through the world of accelerators. A chip was dedicated to one function. It's got all these acceleration techniques necessary to perform the functionality of a very rigorous pipeline of things that you have to do to ultimately turn a three-dimensional graphics command into pixels on a screen. The OpenGL pipeline was very well documented, was very rigorous. We built accelerators to stream out and pump out these beautiful pixels from 3D commands. Over the years, we realized that in order for us to take computer graphics further, we had to make the GPU programmable. And the reason for that is because the artists, the game developers, can't be constrained to a singular way of doing something. They need a nearly infinite palette to express their artistic imaginations. And so we created this idea called the GPU. The programmable shader was invented. And we've seen the revolution that happened when we were able to move from a fixed function accelerator model to a programmable model. The revolution was really, really clear. But that programmable shader wasn't just a normal microprocessor. It had to be invented in such a way that achieved the performance of a fixed function pipeline, but the programmability and the flexibility of a processor. And it took us several generations really to make that successful. 18 months ago, we were getting involved in the wireless industry. And we met this company that had seen the same things that we saw in our industry and made a bold move to jump from accelerator fixed function approaches to modem technology, to a programmable approach to modem technology. Now this technology is called software-defined radio, SDR, and it's been talked about for decades, frankly. However, it has never been achieved successfully. When we met this company 18 months ago, they were the world's first commercially shipping SDR modem, and they were shipping in 3G. They were shipping in 3G. We got so excited about their approach. We got so excited about their team. And we decided to buy this company called Icera. Icera, 18 months ago, became NVIDIA, and starting this month, we are going to be sampling our first modem. It's called the i500. The i500 is an elegant processor. It has 8 modem processors in it. These processors are programmable, and they run the entire modem stack. 3G stack, 4G stack, the Viterbi decoder, the turbo decoders, all the interference algorithms. It runs all of the software necessary to deliver the modem, and it does it in a programmable way. There are 8 processors inside, each of them 160 gigaops, and 8 of them together delivers over 1.2 trillion operations per second. 1.2 trillion operations per second. Now just to put that in perspective, this little tiny chip, it's a modem, remember, this little tiny chip is doing 1.2 sustained trillion operations per second. That's 200 trillion. This little chip is 1.2. Now, of course, the mathematics that it does is very specific to wireless communications. But nonetheless, it's a programmable processor. 1.2 trillion operations per second. If we had to use a general purpose microprocessor to do that, my guess is that our estimate, your fastest, highest performance 6-core Core i7 running a couple of 100 watts couldn't even do it. So we're so excited about this technology. And this month, we are going to be sampling the i500 modem part of Tegra 4. I'm just incredibly excited about that. Now, just to illustrate the benefits of a software-defined radio, or this software modem technology, compare it to the state-of-the-art LTE modem. It is so much smaller, and the reason for that is this programmable architecture was designed for modem technology, and because it's able to reuse each one of the processors for every stage of the pipeline, it doesn't have to replicate these fixed function blocks. Frankly, if NVIDIA today, if our industry in graphics was still using fixed function processors, in order for us to deliver the type of visual quality that we're seeing today, the chips would be many times larger as well. We were so enamored with this technology, we took the chance, and I'm incredibly proud and gratified to say that we are now sampling a 4G modem based on this very technology. Let's give those guys a round of applause. Now, the benefits of this modem being small is one thing. However, don't forget, because it's a software modem, it could achieve things that a fixed function modem cannot. As you know, the world is not all the same, and every single city, every single area we're in has different capabilities for connectivity. When you're in New York City, you're trying to figure out how to reconstruct all of the beams, cellular beams, into a signal that one phone can handle. On the other hand, if you're in the Great Plains of America, you're so far away from a cell tower, you're not trying to do beamforming. There's only one beam. It's coming from about 50 miles away. You're trying to figure out how to extract this little tiny possible signal from the background noise that's always there. And so these different environments requires different types of algorithms for optimization. The benefit of this SDR, just as the benefit of GPUs, there are different things you can do that aren't possible if it was fixed function. SDR allows us to download into the processors algorithms that are optimized for different areas of interference. And we could also improve it over time. And just like software downloaded on your phone, we could use over-the-air updates to upgrade your phone. So software-defined radio, the software modem technology, really, really exciting. And so that's Tegra 4. That's Tegra 4. 72 GPU cores, the world's first quad-core A15, the energy sipping core, a 4+1 architecture. Still has the prism technology that adjusts the backlight dynamically on every single frame in hardware to conserve energy. And then also, finally, also our first 4G LTE modem, Tegra 4. Well, I've got a little bit of time left.